parts. So where are we now? Where, like in the previous sessions, we got to the point of we're splitting up the theorem that the DFA and the regular expression are equivalent, and we express that in terms of a theorem, an if and only if theorem. Let's see which way we go. I can't remember. Was it? We're now in the only if part, and I think the P, if Q, if Q. So we're now proving from the left-hand side to the right-hand side. So if P, then Q. And P, that was the mathematical expression that said that the language is regular. And therefore, the right-hand side would be there is a machine that no, hold on. No, that is, the language is regular, therefore there's a machine that recognizes it. That's the left-hand side. And the right-hand side is a regular expression. So in other words, we have to go from a machine to a regular expression. Yes. Okay. So we're in the middle of doing that now. Okay. So you start with you're given a language. You start with that language's DFA, the DFA that recognizes that language. Okay. And then we have to convert that language into a regular expression. That's the task, and that's the only if part of the proof. Now, we did the if part the other way earlier. I won't go into that. All right, and then from the previous session, we use a two-step process. We go from a DFA, we convert that fairly easily. That wasn't difficult from the previous session. We convert that DFA into a GNFA, so a generalized non-deterministic finite automaton. We add if your DFA has, I don't know, k states, so to convert that into a GNFA, a generalized non-deterministic finite automaton, we add two more states, a start state and an accept state, just one of each. So now this GNFA will now have k plus 2 states, right? And we had made other various modifications. There's quite a list. Okay, so trying to get the big picture. So we convert a DFA into a GNFA, okay, and then and here we're almost up to where we were at the end of the previous board. So we now have this GNFA, and the next step is from that GNFA is to derive a regular expression. And the way to do that, you may remember the last minute or so of the previous board, previous session, was you rip out a random, well, not totally random, I'll get back to it in a minute. You rip out one of the states of your GNFA, and then you repair the damage in the sense that of the labels that are left over, you modify them in such a way that this modified GNFA that now has one state left, right? You ripped out one state and its connections, you rip those out, and then the remaining transition arrows, the labels on them, remember a GNFA, the labels on transition arrows are regular expressions, okay? Not just, they're not restricted to only symbols in your alphabet, like in your input string. Okay, they can be, but there can be more. They can be whole, larger, more complex regular expressions. Okay, so you can repair the modified, the resulting GNFA that now has one state less. by changing the labels on the transition arrows. And in this lecture, well, this board, I'll show you how to do that. And towards the end of the board, so in the 4th session, we'll start doing 2 examples of this process. How to go from a DFA, how to convert it into a GNFA, and then how to shrink, in a sense. You go down step by step to a sequence of GNFAs, each one with 1 state less than the one before, until you get down to a GNFA with only two states, and then you just look at the label on the transition arrow in that 2-state GNFA, and those 2 states will be the start state and the accept state. And the label on that transition arrow will be the regular expression that you're looking for, the regular expression that is equivalent to your original DFA. Right? Remember, we're trying to prove that for a given DFA there's a corresponding regular expression. Or if you go back a step, for a regular language. Because remember, if there's a regular language, there's a corresponding DFA that recognizes it. So if you go back a step further, for a given regular language, there is, well, go the other way, from your point of view. If there's a given regular language, then there is a corresponding regular expression. Okay, hope you followed all that. Alright, so these couple of sessions we'll go into the nitty-gritty, the detail of how to convert your DFA into a regular expression. And in particular, how to correct the damage. When you rip out, you throw away, in other words, a state in your GNFA, how do you repair the damage? What do you do? So that those details we will do these couple of sessions. All right. So words here. So you have you assumed you've taken your DFA, you've converted into a GNFA, right? And assume, let's say, it has k states. If your DFA has, well, let's say m states, your the equivalent GNFA will have m plus 2. The number of states in the DFA plus a new start state plus a new accept state. Right? So it'll be m plus 2. It'll just be 2 states more. Right? Now, by ripping out one of the states, that state that you pull out, rip out, is it cannot be the start state that you just added, or the accept state that you just added. Right? But it can be any one of the others. Doesn't matter which one. But right. So you pull it out. So then your k state GNFA will now become a k minus 1 state GNFA. Right? And k has to be greater than 2. The smallest GNFA you can have is with 2 states, right? The start state and the accept state. And there can only be one of each, and they have to be different. Remember the 3 conditions we placed on the last board on a GNFA, right? Okay, so it doesn't matter which state, except for the start and accept, but any of the other states, doesn't matter which one you pull out. The order doesn't matter. So you pull randomly, you pull one out, and let's call the state that you rip out or pull out. Let's just call it Q rip. Right? You just tear it. You tear it off, throw it away. You pulled it out of the GNFA. So let's call that state Q rip. All right. Now I was saying when you pull out that state, you also rip away, you pull away the arrows to and from that state. Right? Otherwise, they're going nowhere. So the arrows going to the state, Q rip, you remove those arrows, and the arrows going from Q rip, you remove those as well. And then you have to modify the labels on the remaining arrows, the remaining transition arrows, and I'll explain how you do that. So as to repair the GNFA so that it still recognises the same language. So it's still equivalent. Equivalent meaning doing the same job, recognising the same language. All right. Okay. Now, in general, so I'll go on to the next square in a minute. Between any two states, QI and QJ, so two general states in your GNFA, generalized non-deterministic finite automaton. Have a look here. Now this is any state, QI and QJ. They're just two general states. Okay? Now remember from the three conditions that we put on the GNFA, each state has to now, except for the start and accept states, but all the other states, there's a connection from each of those states to all the other states, and each of the other states has a connection to it. So let's look at the state that we're going to tear out. Okay, so it will have an arrow, a connection arrow to it from general state QI. Okay, and it will have an output arrow to general state QJ, and you could have I and J being the same, right, in all cases. And remember also from those three conditions, one of them, or part of one of them, was that each state has a feedback loop to itself, so there's a transition arrow back to itself. So let this be the state that you're going to pull out, and these two are just two other general states, right? Just I and J, so in general.